Hi everyone, welcome back to Module 2. Today we are going into our section on the action potential. So first we have an introduction, and then we'll go into electricity and the neuron, electrochemical gradients, and then a review of synaptic transmission as a whole. So we learned last lesson that neurons have the ability to conduct electrical signals along the axon, and that the axolemma is the name given to the membrane on the axon and is the site of the action potential. So our key questions for today are: what is the action potential and what are the phases of the action potential? The most basic definition of an action potential is the electrical signal that passes down the axon and ultimately causes neurotransmitter release. It occurs through a mechanism of ion exchange across the axolemma. This representation of the action potential moving down the axon demonstrates the efficiency of saltatory conduction, which we talked about in regards to the myelin sheath. So as you can see, it moves much more quickly down the myelinated axon than it does the unmyelinated axon, which can sort of tell you the types of things that can go wrong when an axon is unmyelinated. That's not to say that there are not any unmyelinated axons in the brain, because there are. But if a neuron that is supposed to be myelinated is unmyelinated, then the action potential is conducted much more slow, which can cause miscommunication, which is what happens in some neurodegenerative diseases. But back to just the basic action potential. Something about the action potential that's brought up a lot is that it is all or nothing. Every time an action potential occurs, it has the same amplitude. There are no smaller or larger action potentials, and basically you feel things more strongly due to spatial or temporal summation of action potentials in the brain, meaning that a stronger stimulus will produce more frequent action potentials, or it will activate more neurons. So we are going to walk through this chart, which you'll see a lot in studying the action potential, and we can break it down into three phases. We have the rising phase, the falling phase, and the refractory period. Just a quick note on these numbers. So -70 is what's known as the resting membrane potential. So we know that the action potential is an electrical signal, so it's going to have something to do with different voltages, and we'll talk more about what that means in the next lesson. But just keep in mind right now that this -70 is -70 millivolts, and that is the resting membrane potential. So when the action potential occurs, there is some kind of stimulus that causes the membrane to depolarize. Depolarization means that the membrane potential is becoming less negative. It's moving towards zero. And it's caused by an influx of positive molecules into the axon. When the depolarization reaches a certain threshold, the membrane potential changes rapidly until the peak of the action potential. And so, obviously, in order for an action potential to occur, there has to be a suprathreshold stimulus. And then when there is a subthreshold stimulus, an action potential does not occur. And you can see that in the failed initiation. The ions that move into the axon are sodium ions. And again, size of the action potential does not change with the magnitude of depolarization. So the next phase is hyperpolarization. And this is basically when a different ion, which is a potassium ion, rushes into the axon and causes the membrane potential to move back towards zero. It causes it to become more negative. And this is called repolarization. It's the opposite of depolarization. You depolarize and then you repolarize. And then what happens next is called hyperpolarization. And this is when the membrane potential dips below resting potential. And so the neuron goes into what's called a refractory period, which is when it cannot fire another action potential. So let's say you're studying signals from a neuron or a group of neurons, and you're trying to figure out if a particular signal came from one neuron or not. You can look at what's called interspike intervals. So this is the expected refractory period that you would see from one neuron. And if there are violations, if there are signal artifacts in the refractory period. This is called an interspike interval violation, and that can tell you that whatever it is you're looking at is not just one neuron, it's probably multiple neurons, or it's noise or something. So that becomes really important in understanding and reading spike processing and spike sorting outputs. So very important. Next we have, yes, we talked about this last time, how there can be excitatory and inhibitory signals. An excitatory signal is more likely to bring the next neuron to threshold and therefore is more likely to pass along the signal. And the inhibitory signals are more likely to hyperpolarize the next neuron, which brings it further from threshold and it stops the signal. This image here is just meant to show you the different ways that organization of excitatory and inhibitory neurons can act as feed-forward or feedback loops in order to enhance the complexity of the things that the brain can do. So that is all we have for this lesson, because I think it covered a lot. So we know that the action potential is the electric signal that passed down the axon lemma when the neuron fires. It takes place in 3 phases that are associated with an influx of different ions that changes the membrane potential. The first phase is the rising phase, and the membrane is depolarized. After the peak of the rising phase, the membrane is hyperpolarized in the falling phase. The neuron then goes into a short refractory period in which the axon lemma is hyperpolarized below membrane potential. A neuron can send excitatory signals or inhibitory signals. And next, we will cover the role of electricity in the action potential.